all up for you. I give it 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 all up for you. Yes, 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 I would. Totally broken hearted, guilty of what I did to you. Lately since we parted, I truly know that I need you. Yes, I do, because I give it all up for you. 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 Yes, 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 I would. Come on. I really love you. Come on, I give it all up for you. 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 Yes, 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 I would. Yes, I would. Yes, I would. Yes, I would. Hey, yeah. Yes, I would. Yeah. Yes, I would. Something got me started. Hey, something got me started. You got to 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 something got me started. Take it out. I love you. Show me. Something got me started. You know that I will love you. Lately since we parted, I truly know that I need you. I give it all up for 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 you. Yes, 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 I would.
Good afternoon, everybody. My name is Gert van Wyk. I'm the marketing manager of Bosun, the sponsor of today's event or webinar. The presenter, Dave Hine, is no stranger to us and South Africa. He's presented an introductory webinar last year. Also, on behalf of SAICI, today is a follow-up on that initial webinar. We're going to delve into a little bit more details because I think it's permeable paving is really something for South Africa's future. So without any further ado, I'll hand over to Dave Hein. He'll tell you more about himself as well.
Great. Thank you very much, Kurt, and welcome everyone today to today's session. As mentioned, my name is Dave Hein. I'm a civil engineer. Well, first of all, let me apologize in advance I'm just getting over COVID, so I tend to cough once in a while, so I'm going to try and make sure I catch myself and mute myself before I do, but I'm too slow, I apologize in advance. So I'm a civil engineer with 38 years of experience in design, evaluation, management of transportation infrastructure, and particularly pavements. I come from Canada. I'm the past chair of the Transportation Association of Canada Pavements Committee and do a lot of work with that group. I also represent Canada on the World Road Association, originally the Pavements Committee, and currently I'm with the Asset Management Committee. In the U.S., a lot of my work has been in the United States as well. I've recently retired from a company that was founded in the United States, and spent a lot of my time down there, and a lot of work with the American Society of Civil Engineers. Was the president of the Transportation Development Institute. Did work with them in developing a standard for permeable interlocking concrete pavement back in 2018. Also a member of the Environmental Water Research Institute, EWRI, which is part of ASCE. And EWRI published a book in 2015 called Permeable Pavements. And we are currently in the process, in fact, I had a meeting yesterday to update that book with new things that have happened over the past 5 or 6 years or so. So that should be published early next year, I would say. Completed numerous webinars and workshops and training sessions related to permeable pavements. I've been doing this for the last almost 20 years probably, and have seen a huge development and growth in permeable pavements, not only in Canada, the United States, but around the world. And in fact, we're not the first ones to this at all. We've seen this being used in Europe for many, many, many years. So there are 3 primary types of permeable pavements: pervious, which is pervious concrete; porous, which is porous asphalt; and permeable pavements, which is what is used typically to call interlocking concrete block, or sometimes brick pavements. We also have a lot of other different types of materials where the blocks themselves are permeable. We have grid pavements. We have a lot of different permutations and combination of them. Ultimately, their goal is to infiltrate water into the surface and act as a stormwater management tool. So instead of having a pavement surface shed water from the surface, and so we have to deal with it with underground piping systems or ditches and stormwater ponds, we're trying to deal with the water at the source and get it into the ground, back into the ground. They are a green infrastructure solution. Of course, everybody's interested in sustainability and green infrastructure and reducing carbon footprints and things like that. Water has become a very, very important resource in many areas, including where I live currently in Canada. We're on a major drought here, and we get the majority of our water from groundwater sources as opposed to lake sources. And so I have very strict restrictions in my subdivision where I live. I can water my lawn for 30 minutes once a week. Our water bills, what I have here, are 4 times what I used to pay not 200 kilometers from here, where they have access to lake water. And so people are very interested, and there's many permeable pavement systems, in fact, in the subdivision where I'm sitting right now. We are getting water back into the ground. We're obviously helping stormwater and reducing things like erosion from happening. Stormwater carries with it pollutants from the road systems, from other areas, from farm fields and things like that. And so they increase nitrogen and other chemicals. And so by infiltrating them into the ground, we're not getting them into cold water streams, for example. Reducing erosion is obviously an important thing as well. That photograph you see there is from the Boston Logan Airport in Massachusetts in the United States, where they have a number of different systems of permeable pavements around the airport, as well as internal to the airport and their road infrastructure and their parking systems. It reduces combined sewer outflows. In many areas in North America, we have older areas where we've combined sanitary and stormwater systems, and so when it rains, all kinds of nasty things get floating down into the lakes and rivers. So we can try and separate those things from happening. We can help support tree growth, because a permeable pavement system doesn't have the same dense aggregate materials and things that we would normally use with pavements. And so tree roots are able to grow into the spaces a little easier. They have direct access to water. And a couple of my projects in the US and California have shown improved tree growth and tree canopies, and therefore improved oxygen generation and things like that as well. Improving character of the neighborhood. Lots of signs go up talking about permeable pavement systems and what we're doing to help infiltrate water, and all of those things are looked upon very positively. General components of paper. I just should mention briefly about how I was going to go through this. I'm going to give a basic introduction of permeable pavements. Some of you may have seen some of this already. I'm going to get into a little bit of the design aspects of it. We're going to talk about a design application called Permeable Design Pro that really recently has been developed for use now in South Africa. And then I'm going to talk about a little bit of construction, a little bit of maintenance activity. So all the key components to help ensure you have success in building permeable pavement, designing and building permeable pavement systems. Basic components of them, they're like any other pavement, except that we're using different materials as support for the pavement structure and the loads that we apply to them. We are using open graded aggregate materials. Sometimes we're also using other things like plastic boxes and things like that to make a larger ability to control water in the pavement structure. We are using open graded base and sub base, open graded bedding layers for the pavers. And the pavers themselves, while they are solid concrete materials, like we would build any other paver, they have wider joints in them, and we no longer put sand in the joints. We put aggregate, chips of aggregate in the joints to allow water to infiltrate through those joints in between the permeable paving systems. We have three basic design principles. We have the full infiltration design, which is this one, where we have sandy soils, more ability to permeate water through them. And so we basically allow the water to go through the pavement and directly into the groundwater source below. So while it's doing that, we're cleaning the water to some extent, and we're also basically recharging the waterbed and the water tables below. We have a partial infiltration design, which is primarily the majority of many locations, because these are pavements that are designed to store as much water as we can. But because the subgrade soils are not very permeable, we can't get all of the water necessarily into the ground. And so what we're doing is we're allowing as much water into the ground as possible. And as the water builds up in very significant storm events, then what we're doing is storing it in the pavement as long as we can. And then at some point, we don't want it to overflow the pavement. And so we put in a drainage system that's hooked up to allow water to be removed from that can't get into the ground system. This is a very popular pavement design process we use in areas where I am. So the pavement, the water in the pavement will get up to the point where we have an outlet, and the outlet will then take the water to a stormwater pond or a ditch system or whatever. The last design process is basically a no infiltration design. And so in this particular design, we basically cover the entire permeable pavement system in an impermeable liner. That liner will not allow water to go through it. And so there are two primary uses of this type of system. One is to save water and store it. So we will keep it in the pavement structure. We will typically put a cistern, some other way of a larger area to store water. We'll move the water into that cistern, and then we'll pump it out and use it as gray water, plant water for other sources. There are some places that are actually storing that water for reuse for human consumption. So the water is then cleaned, of course, when you have areas that have very small amounts of waterfall. And then the second use primarily is for situations where we have gray or brownfield developments where we're redeveloping something where there may be some contaminants in the groundwater. And so we don't want to add water going through that. So we're basically separating the permeable pavement system from the subgrade below such that we're not increasing flow that will move some of those contaminants to another location. And I see a lot of these in some of the brownfield developments in the UK, for example. Different types of permeable pavers and their applications. Typically, the most common application is a solid paving stone that's manufactured in a plant of very high pressures, very high compressive strengths and flexural strengths. And we have the spaces between the joints, as you can see here. This photograph is from Colorado. It's at a beer factory where they make beer, basically. And so they drive the beer trucks with the beer kegs and stuff across these permeable pavements. So parking areas, roadways, we see a lot of roadways in Europe who have had much more experience with permeable pavements than we have in North America. We're starting to see a lot more roads in North America being built with this. Major advantages in terms of construction, because we no longer have drainage systems under the roadway that are piping and going to catch basins and going to piping systems that are removing it and taking it to a stormwater pond, for example. And so construction is easier to facilitate. We don't have all these trenches that potentially could settle. And so contractors love doing this. And then we basically infiltrate all of the water we have through the pavement and then deal with it once it's in there, whether we infiltrate it or take it someplace else as well. So you have things like roadways and alleyways you see here is a very, very common use. This is a project I did back in 2015 in California, in the San Francisco Bay. So this was an existing roadway that we reconstructed. So we kept the curbs and the sidewalks. We excavated the old roadway out of there. We prepared some berms I'll show you later and how to control water because this is on a slope. And then we built a permeable pavement system. So this was primarily done by this particular city in Berkeley, California to improve the water quality potentially in the San Francisco Bay Area. A small contribution at the beginning, but of course, as you build more and more, you're going to make larger and larger contributions to it. Lots of parking lots. Pictures you see there on the left is a conservation area close to where I live. The one on the right is a design-build permeable pavement that I did with another local contractor in Hawaii, in Oahu. Bottom left is from a car dealership down the street from where I live. Bottom right is from Boston, Massachusetts, near the airport, near the Atlantic Ocean. Lots of different locations. The one on the top left I took 2 weeks ago in Germany at a long-term care home where my wife's relatives are located. The bottom right is actually the Rhine River is immediately on the left there of that vehicle. A lot of the parking lots that are adjacent to sandy areas like the Rhine, the Mosel in Germany, for example, you'll see a lot of permeable pavement systems. The top right is actually a porous asphalt system, again, close to where I live. This is from a botanical garden near where I live. They're doing sidewalks, alleyways. The left side is from Florida in the U.S. Richmond, Virginia. This is in Longmont, Colorado. The one on the right side, it's been there for 10 plus years. I was involved in Colorado Springs. They have regular pavers for the sidewalks, and they've got permeable pavers between the tree pits. So we get water infiltration there to be able to water the trees, which is also quite good for the trees, of course. Driveways and houses, we get credits here on our water bills when we have permeable driveways in our house. We get penalized for having hard surfaces. So the roof of my house, for example, I'm penalized. All of the water that lands on the roof of my house goes down the downspouts and it goes into an underground infiltration bed beneath my foundation of my house. Again, because we get all our water from the groundwater. So no water leaves my property. So we get credits when we have permeable driveways or sidewalks or decks behind the house, or I've got water barrels here as well to reduce the amount of water that we use, the fresh water that we use. And so those are very common uses. Where my wife takes the cat, this is a veterinary place. The driveways, all of the areas around from this property go onto the permeable driveway and then get infiltrated into the ground. We see them at schools and universities. This is from Portland, Oregon. Been there for 12, 14 years now, I think it is. I was involved originally when this was constructed a long time ago. So lots of applications in lots of different places around the world, certainly. Keys to a successful project. Some of the things I'm going to talk about are ensuring that we're going to have success in building our permeable pavement system. And so ultimately, first of all, I think it starts with is ensuring that we're carefully considering the conditions of our site, our potential limitations, things that we can use to remediate, potential risks associated with building a permeable pavement and then having it not function potentially. We do two types of design. We do pavement design like we would normally do to handle the vehicular traffic that we have, and it's very similar to what we would design with conventional pavements. And then we have hydrologic design. So we're combining the water flow and how do we get the water into the pavement? Where is it coming from? How do I move it in the pavement, get it into the ground? Do I get it into piping systems? Do I move that to someplace else? So all of those things are very, very important at the design stage to ensure we're going to have success. We need to have very clear, precise specifications. Now, all of the industries typically have some guidance in terms of specifications for permeable pavement systems. So those that build asphalt or concrete or or pavers or bricks or grids, all have some guidance in terms of specifications. And those have been developed over many years of experience and trials and improving on how we build them. And so it's really important to have a good set of rules, obviously, to follow, for the contractor to follow. Pre-construction meetings are important to ensure that everybody understands, especially in areas where this is new. So when I was first doing this 15 years ago, we would insist on a pre-construction meeting. We would insist on a pre-build to show the contractor is capable of building something, and we've gotten more lax about that because we've got more and more people experienced in doing this and understanding that you don't drive dirty trucks all around your construction sites. And the picture there is actually from a permeable paver section in Calgary, Alberta, in Canada. And what they did is they used rails actually from trains and built basically a cattle guard. So this is, you would see them in ranches where you've got a galvanized metal piping systems to prevent the cows or the cattle from going out of the fence, out through the gate. And so these also serve to shake the vehicles as they go in and knock some of the dirt off of them. So things like that are very simple, to make happen. Having proper construction inspection, like any pavement, is important. Keeping the site clean, I've already mentioned, and ultimately it's the little details that really count to ensure we're going to have success. Some of the basics of permeable pavements. Number one is that we have pavers that can be constructed of various thicknesses. We can have 6, 8, 10, 12 centimeter, even bigger thickness of pavers. And 6 centimeter pavers are something that we only use here for pedestrian applications. We will never drive a vehicle across a 6 centimeter paver. 8 centimeter is our minimum recommended thickness for ability to develop shear resistance between the pavers so that we're able to provide loading that's going to be transferred from one to another, and also for the structural capacity. So typically 8 centimeter minimum for vehicular pavements.
David, we've lost your sound.
Uh-oh. You hear me now?
Better, yes, thank you.
Okay, sorry, apologies. So 45-degree herringbone is important for stability of the paving system itself. 90-degree herringbone possibly as well, but these are the patterns of pavements that we've learned that are more stable under vehicular traffic. And so there's so many different kinds of pavers. Different ones will provide a little bit of different stability than others, but typically it's the laying pattern and the jointing that is going to provide most of your structural capacity. The jointing needs to be consistent, uniform, and tight. So we want to ensure that we're getting the majority of the shear capacity that we can get. We want to use proper jointing material and bedding material that is hard, durable stone chips that aren't going to break down under loading and that, again, provide shear capacity. And then installation quality is the quality of the construction work that we do. So how are we going to install them properly with all the layers? How are we going to compact them? And we're going to talk about that as I walk through the webinar here today. Design features. We need to know about traffic type, configuration of the vehicles. What kind of vehicles are we designing them for? Both of these two pavements you see in the pictures there on the left is a tank, M1A1 Abrams main battle tank in Colorado Springs that I designed a permeable pavement for. The one on the right is the Olympic Village in Vancouver. This one, it was designed, they built it so that the construction traffic, we were using it at the end and we didn't like that. But ultimately they were late for the Olympics, so we had to make some compromises. But ultimately, we designed them for the intended traffic and what they are. For the most part, most of the permeable pavement systems are designed for light vehicles, occasional heavy vehicles, the garbage truck once in a while, a school bus or something like that. And those are relatively straightforward. If you're doing anything like I'm showing in these two photographs, find yourself a decent pavement engineer who's done this before and understands what it is to develop permeable pavement systems for heavy vehicular traffic. Drainage is important. Obviously, we are dealing with water. Water will find its way someplace. It'll find a place to go. It always does. And so we don't want to have catastrophic failures like you see in this particular pervious concrete system, where they had issues with the underground drainage and they didn't build the berms properly and a whole bunch of other issues related to a failure of the pavement, literally. And so understanding that, we can design for this. It's not difficult, but we just need to make sure that we do it and do it well. Other features, contaminant loading. 2 permeable pavement systems we see here, one during construction of a townhouse complex in California on the right, and we're not protecting the permeable pavement from water running around and taking dirt onto the surface, which is not a good thing. The one on the left is in Calgary, Alberta, and this was a demonstration site, and they use very large, they don't use winter sand in Calgary, they use chips. And so this is basically inundating the permeable pavement surface and not really doing too much damage to it, but still not the best ultimately. So we want to prevent things from getting washed onto the pavement as much as possible, coming from trees above, of course, as well, potentially. Some of this stuff breaks down and it might clog the joints, and then we have to do some maintenance to reinstate the permeable pavement system. So site characteristics are really important to decide where and when you actually build the permeable system. So site design. So this is that Environmental Water Resources Institute book from American Society of Civil Engineers on the left, Permeable Pavements it's called. I was the editor of that, and I'm currently a reviewer of majority of the chapters of this book that we're doing to update this. And it's got some great guidance in it in terms of checklists. And so these are for every aspect of the design, the construction, and the maintenance activities. And so for things like overall site characterization, we have location where we're doing this. Why are we doing this permeable pavement design? Are we doing it to clean water? Are we doing it to carry water away? Are we doing it to infiltrate water? What is surrounding our area? What is the hydraulic conductivity of the soils? What kind of risks are we taking, and how do we at the design stage apply risk factors that will discount the amount of infiltration, for example, into the ground, because we're expecting it to have some contamination, and so we design for that right away up front. And so we're designing it at square one. We're reducing the allowable infiltration into the ground. It will infiltrate faster until sometime 10 or 15 years from now when we may slow down. So we account for that. Are we having water run off the surface? What kind of capacity do we have? How much water will pond on the surface? Maybe in a very high storm. I'm doing some alleyway designs in Texas right now where, it's fine for everything but a 100-year design storm where we may have about 20 millimeters of water ponding on the surface for 40 minutes during the 100-year design storm, during a hurricane, basically. So, and we have criteria for all of this, of course, to be able to make this happen. And then how long does it take the water to drain out of the permeable system? Geometrically, continuing with that, do we put in subdrain systems? To carry water out? Do we target water quality enhancement? Do we detain the water for a longer time to let gravity filter out some of the contaminants in the water potentially? We put sand filters in some of our permeable pavements to actually do what an actual water treatment plant would do to filter the contaminants out of the water stream, because we don't want them in the water that go where the fish are. We'd rather have low-level contaminations in the permeable pavement area than let it roll right into the cold water stream, for example. And then we consider potential failure areas and mechanisms like edge restraints and overloading due to maybe heavier vehicles using the site and things like that. Geometrically, we look at all kinds of elements related to the use potential of things like geotextiles or underdrains or supplementary drainage features that take overflow on the pavement, for example. Are we going to have subsurface detention of the water? How long are we going to detain the water? Usually we design for 24, 48, 72 hours, so we'd like to empty the pavement within 72 hours. It may be different in an area that has frequent rain or an area that has very little rain. And so all of these things are taken into account. And if you're in a frost area where you've got cold, wet environments, we have freeze, then we also need to do some things to make sure we don't get frost heaving and things like that happening. Subsoils, we do geotechnical work like you would with any regular pavement design, except for we include hydraulic permeability of the subgrade material. And then we'd like to know where the highest groundwater will be. We typically don't want the bottom of the permeable pavement system to be within 0.5 meter to 1 meter of the highest groundwater level we have. It kind of defeats the purpose of it. So ultimately, all of these things are in these checklists. We have a bunch of decision factors. This comes from the ASCE standard. So this was a group of 20 hydrologists and 20 pavement engineers getting together to develop the permeable pavement system and the manual that we have from ASCE. And so we consider things like longitudinal slope or transverse slope. We consider potential for contamination of spills for happening, for example. Are utilities present near the pavement surface, and do we have to protect those from water? We look at all things like volumes of water, multiple design storms, multiple storm events that may be back to back. Again, all of these things are dealt with at the design stage. Do we have complex geometric conditions like water shedding off of a building roof, coming from a soccer field pitch, for example, or from a parking area, or a non-permeable surface rather, et cetera, et cetera. So lots of different considerations that we use. And I mentioned depth of water table and chemical spills as well. We have tools for some of this that were developed as a part of research programs that I was involved in with the National Cooperative Highway Research Program in the United States. And so we have spreadsheets that are basically risk matrices. And so engineers like spreadsheets. And so we develop criteria. We weight the criteria and as to how it may positively or negatively affect the permeable pavement system. And then we rank it. We put criteria A, B, C, or low, medium, high, and we answer the questions, fill in the blanks, and at the bottom right, you get a go, no go type approach. So if it's red, it means don't do a permeable pavement here. If it's green or green, it says, yep, do one here, no problem at all, the risks are low. And if it's yellow, it's, yeah, you could consider it, but maybe you should consider your risks. So we look at potential sites, we evaluate them. We look at the criteria is not always the same. It's different in a municipal environment than it would be a recreational environment or something like that as well. So we look at things like underground utilities and when the last time they were replaced. And some of the elements are the same thing you would do with any normal pavement design, but in some cases we want to make sure that we're dealing with permeable situations. And so we look at a variety of different road systems. This came from an actual project. And this Alston Way was the road that was built at the end of the day. So it helps to give you some logical criteria to help evaluate risks associated with permeable pavement systems. So let's get a little bit into the design aspects of this now. So permeable pavement design. And there are lots and lots and lots of guidance related to permeable pavement design around the world. So I've got some here from the US, from New Zealand, from the UK, from Canada, from some of the US states, from industry associations like the Interlocking Concrete Pavement Institute, for example, ASCE. This has gotten substantial. I could give you pages and pages of these things now related to permeable pavements, and many organizations on a state level or a municipal level, a city level, will have some of their own guidance related to permeable pavements as well, and conservation authorities as well. We have two sides of it. I'm going to just go fairly much through the highlights of the design process here, and show you how we do it with the software application, Permeable Design Pro. So we have two sides of our design. On the left-hand side, we have a structural analysis. And so that's very similar to what we would do for any pavement design. This could be anybody's pavement design processes that are used in South Africa or whatever, Israel or Australia or whatever, US and Canada. And so structural design is very similar. There are some of the factors of the structural capacity that we modify because permeable pavements aren't quite as strong as conventional pavements, and because we open the spaces in the joints. And then we have a hydrologic side on the right, which basically is balancing the water. So we need to balance both of those two. And if we balance them both, so the pavement is just thick enough to handle the strength of the traffic we have, and we have just thick enough to handle the water and achieve the water goals that we have an optimized system, which is good. So we have the primary method that is used in North America is the AASHTO method. It's called American Association of State Highway and Transportation Officials. It has been the standard pavement design process that's been used for most North American agencies and others around the world since the 1960s. That's being changed now towards mechanistic design, but we'll talk about that in a moment. So what does it need? It needs traffic data. So we need to know what traffic are using our pavements. Basic information are types of vehicles, the axle loads on the vehicles, how much weight is on the vehicle, axle loads, and ultimately, the better the information you can get, the more precise the design can be. We typically do not design pavement systems for passenger vehicles. We design them for heavy vehicle traffic. So this may be trucks or lorries or bus traffic or fire trucks, as you see in the lower photograph there. And we take the axle loadings of each of these vehicles and we convert it to a standard axle load. So a standard axle load is called an ESIL, equivalent single axle load, and it's not a linear relationship, it's a power 4 relationship, which allows me to convert the actual loads on the axles, be them a standard axle load or below or higher than the standard axle load, into a common number, a common design numerical value. So that's what's called the ESILs, or the design ESILs of pavements. The design easels are usually estimated based on the vehicle types we have, depending on they're a local delivery van or a dump truck or a 18-wheeler type vehicle that has transports major goods between major city centers, for example, or on the highways. And so we need some basic information about our vehicles. We need some basic information about our materials, and particularly the ground on which we're building them. Virtually all pavement design procedures use resilient modulus, which is the strength of the subgrade material, as the input component for the pavement design procedure. And so these input values, if you'll hear things like California bearing ratio, you'll find R values, you'll see DCP, dynamic cone penetrometer values, you'll see FWD, falling weight deflectometer. You'll see lightweight deflectometer, like this particular one here, which we do use a lot for permeable pavements. And these help us to characterize the in situ soil materials and potentially the base and sub-base material. So number one, we need to know its strength. And so again, we divert to resilient modulus values. And if you're using other methods of characterizing it, typically they're converted to resilient modulus anyway. And then we add one more thing. The one more thing is basically the subgrade infiltration rate. So how much water can we get into the ground? And so this is usually done by a single double ring infiltrometer. You can see some of the new site here where the testing is being done in situ, and the permeable pavement is going to be built on top of this. In California, we excavated trenches in the road that we were going to remove, and we literally did infiltration tests directly in the road infrastructure before we removed all of this material during construction. And so that allowed us to get a good handle on the infiltration rate in situ in this reconstructed road location here. So we then apply some safety factors, what's called reliability or serviceability index, that are used in this AASHTO design procedure to basically come up with the input values that we need for a structural design. And so we need to know how many easels it's being designed for. And in terms of easels, to put it in context, I guess, my driveway would probably be designed for 50 to 100 easels over its life. The roadway in front of my house is a low volume local roadway. It would maybe be designed for 50 to maybe 100,000 easels. We get some garbage trucks, we get some recycled vehicles, we get a few construction vehicles, things like that. The collector that takes from my street in front of my house to a larger arterial road would probably be designed for 1 million, 2 million easels. The arterial road, the major roadway that has 4 or 6 lanes that moves traffic from my subdivision, will be designed for 15 or 20 million easels. If you get into highway traffic, you could be talking 50, 100 million, something like that. Most permeable pavement systems are designed for less than 1 million easels. In places other than the UK have been designing them regularly for 10 million easels. And so again, you need some different designs. I know they've designed stabilized bases in Belgium and other places in Austria and Germany as well. So you can design them for heavier traffic, but majority are typically less than 1 million easels. So low volume residential roadways and down to parking lots and things like that. And so we have subgrade modulus, we have factors that relate to smoothness, and we have some statistical reliability factors as well. And so you plug these all into a big equation, which I won't show you, and you get a strength value of 63 millimeters. So I need 63 millimeters of strength, called the structural number. So how do we get the structural number? It's thickness and stiffness. So the thickness is obviously how thick the pavement layer is. The stiffness is a function of its resilient modulus. And so in the AASHTO design procedure, they converted all of the resilient modulus values to stiffness factors they called layer coefficients. They're just a numerical value that represents stiffness. So if you have regular asphalt, you may have a structural layer coefficient of 0.42, 0.44, regular granular dense graded base, maybe 0.14, 0.15, something like this. Permeable pavements typically have a lower structural layer coefficient and therefore resilient modulus because they're open graded nature. They don't transfer load the same way that conventional dense graded base materials were. And so we have to multiply the thickness times its layer coefficient to give us the strength value. And when you sum them up, in this case, 63 millimeters, the thickness of my pavement is now determined. So I need 130 millimeters of 8 centimeter paver and 50 millimeter base. we need a 10 centimeter base structure and a 30 centimeter sub-base structure. So that's the simplicity of the AASHTO design. This has been superseded in North America with what we call ASCE standard 6818. A6818 was developed to move into a more mechanistic design process. And so in order to do that, some testing was needed to look at the long-term impact of vehicles, loadings, easels, on pavement structures. And so as a part of the development of that standard, we commissioned a research study at the University of California, and they have an accelerated load facility device actually that was manufactured in South Africa, of all places. And that accelerated load facility was used to test pavement structures. And then through that testing and the development of rutting, which was this failure criteria, for wet and dry pavements, we were able to develop some design tables and a design methodology that we incorporated into the ASCE standard that is now based on mechanistic design. So we had no easels, we had axle load spectra for traffic, we had rutting as our failure criteria, 25 millimeters of allowable rut depth. We can choose 50, we can choose 75, we can choose whatever we want, but ultimately we've simplified it by running the analyses and developing these design tables. So these design tables are what's included in that ASCE standard now. So we did not to go through the great detail of all of this, and I'll show it to you live in the software in a minute. I'll show it to you in the software in a minute. But ultimately, what we need is we need to know how many days the subgrade in a permeable pavement will potentially be wet. Because when the pavement is wet, the subgrade is wet, it has its lowest load carrying capability. When the pavement is dry, it's going to be able to carry more loads. And so therefore, the number of easels that it can carry when it's dry are much higher than the number of easels it can carry when it's wet. How do you define wet? Wet means that there's water potentially ponding on the subgrade surface. And so the subgrade may, if it's sand, it may be infiltrating water, so very rarely is it wet. It will always get it through very quickly. But a clay subgrade may have water sitting on it. And so we figure out how many days, due to the rainfall distribution during a year or multiple years, could there be water that cannot get into the ground? So that's considered to be what's called a wet day. So we look at the number of days when they have standing water. We take the rainfall distribution in an area. We look at 365-day average rainfall numbers in each day. Then we sort it from the highest to the lowest. And then we basically use the location to determine how many days is it potentially going to be wet, and then we apply some correction factors and some safety factors, et cetera, to that to come up with the answer. And again, I'll show you how the software does it. So this is a design table where we go into the table to come up with numbers. So for example, this is 200,000 easels, and we have 10 to 29 days when the pavement could be potentially wet. The subgrade support capability when we have wet subgrade, in this case, is 24 megapascals, which is pretty soft clay material. And when we run it through our model, we come up with 315 millimeters of subbase. All of these pavements have at least 100 millimeters, 10 centimeters of base. And in this case, we've got 315 millimeters or 32 centimeters of subbase is the answer. So that's how we do our structural design for the permeable pavement system. So you can go to the standard and you can use the standard itself, which you see a picture on the left. That standard, you can use the tables that are in the standard to do exactly that design. You need to know what the wet days are and your location and things like that. And so we've simplified that and incorporated that into a software system called Permeable Design Pro. So Permeable Design Pro was developed in 2010, so it's been around for quite a while, 2009 actually. And it was developed by the industry, the interlocking concrete block pavement industry, to assist designers, and particularly landscape architects, and those not so technical on the engineering side, to be able to do permeable pavement design. So up until 2018, the only design process in there was the AASHTO design process. Once ASCE 6818 was developed, we then took the methodology and we incorporated that into the Permeable Design Pro program. So it is used extensively for permeable pavement design. It integrates structural and hydrological design. Stormwater databases exist, and it started out only Canada and the United States because this is the territory of ICPI, primary territory. And so we took the climate models in the United States and in Canada for Environment Canada and for the National Oceanic and Atmospheric Administration in the US, and we made it so that you could pick cities out of the Canadian states or Canadian provinces and American states. You select it, and you've got the rainfall distributions. Then about 10 years ago, New Zealand was very interested in doing this, and a local contractor wanted to develop and have the software to be able to be used in New Zealand. And so they paid for basically the development of the climate models, the climate information for New Zealand, which also incorporated global warming into it because they modified their rainfall distributions. And then recently, Boson has generously paid for the development of the South African database. And so we've got this from the South African climate folks and interfaced with them to help us develop the models for major cities in South Africa, for the major locations in South Africa. They're not all of them, they're select numbers of them, some of the more major centers, but it gives a pretty good distribution across South Africa now as well. So that has recently been released in the software system. So it's South Africa is up and running, basically doing the same thing we do in New Zealand, United States, and Canada. It integrates hydrologic and structural design, which I mentioned before. We look at the area of where we have our permeable pavement. In this case, the street is the red area. We've got several contributing areas from the park, from the school sidewalk that's on the bottom, you see green, from the adjacent roadways, water going onto the permeable pavement roadway. And we characterize those in Permeable Design Pro by calling them contributing areas. So we say, what's the length and width of our permeable pavement, or just the area of our permeable pavement? So we know what the infiltration area can be, and then all of the supplementary areas that will shed water onto the permeable pavement during 24, 48, whatever, 72 hours. We characterize those areas by how big are they, how close are they to the pavement surface, what is the surface? Is it hard, aka a concrete sidewalk, or is it a soccer pitch, or is it a grass field, or is it a playground? And we characterize the roughness of the surface. So when water falls on concrete sidewalks, it will flow quickly to the permeable pavement. When water falls on grass, some of it will evaporate and some of it will move to the permeable pavement, but at a much slower rate. So what we want to do is develop complete water balances for our design. And so that's what Permeable Design Pro does. Subgrade, we basically have default subgrade types in the system. Everything you see in yellow is a default from the system. And so you can select one, and we encourage people who are doing preliminary design, you can go ahead and select one of these types because we have information about its resilient modulus, information about its permeability, its density, all of that kind of stuff stored in the system. But if you're actually designing one, doing a detailed design one, you should do your own physical testing of the materials, the subgrade, the properties of the material, standard lab testing, basically, and then enter that subgrade into the database. So in this case, you see a list of soil classifications. And then in my database, I have another, 20 or 30 different projects that I've developed the input parameters for those specific locations or areas, and they stay in my database then forever. So it's basic information about the soils. We need to know about the infiltration rates for the infiltration rates of the soils and all of the other materials. Infiltration rate through the surface, the base, the bedding layer, the base, the sub-base, because we have to get the water in. And if we can't get the water in, we can have the most permeable system below, but we need to get the water into the surface as well. And so what we do is we identify the infiltration rates, and then we actually factor them down. So we put a safety factor on, usually a factor of 2. So we reduce the permeability of the soil by a factor of 2, assuming you're going to get some dust deposition and things like that that are going to reduce the permeability of that particular material. So the subgrade properties, other information is bulk density, specific gravities, porosity, so permeability information, and then we can have a long-term permeable. We have a safety factor in the bottom there, which says decrease the permeability by 50% in the long term, and start with that today when we build it, because we think we're going to get some clogging in the subgrade, reduction in permeability in the subgrade potentially happening. So we have resilient modulus information, we can have CBR information, we have lime rock bearing ratio, we have DCP, we've got other things that you can enter to help quantify that material. And then we can also apply a long-term reduction in the modulus of the subgrade as well. So if we think, it's going to be wet all the time, 365 days a year, then it's taken care of by the ASCE method But if you're doing the Astro method, you can discount your subgrade strength by whatever you want, 20%, 50%, whatever you want, to again apply another safety factor to it. Granular base and subbase layer, we have basically the combination of, we typically consider the surface, the pavers, and their bedding layer one component. And so we use a composite modulus of those two layers, and we assign that to the paver system. The modulus you assign is based on the shear capacity of the pavers. If you've got wider joints, you will have a lower modulus than you have with narrower joints. What kind of materials are you using in those joints? Are you using limestone, which is very soft and prone to breaking down, versus granitic materials or other kinds of gabbro, metagabbro, different kinds of rock materials? So depending on what you have in your area. And then the granular layers we combine into a base and a subbase. And we typically have a minimum base layer. So even if you're building a walkway, you're going to put some granular base supporting your permeable pavement system and acting as a storage reservoir for water as well. So those are the systems. And then from that, we basically need to know what's your grading limits of that material. So we want to know what is the highest and lowest gradations of those materials. We can enter the grading limits on this screen you see here. It'll select either the mean percent passing, or it will take the lower and the higher limits of gradation, and it will divide it by 2 and give you the mean for use in the design purposes. And so I looked at some of the aggregates in South Africa that are available that was provided to me by Bozen and Gert. So I looked at them to determine if they're somewhat similar to what we use in North America, where I have most of my experience, and made some recommendations into which kind of aggregates should be used for base and subbase layers, as well as the bedding layer as well. And so they're a little bit different. So the ASTM number 2 is what you see we use in North America, and what you see on the right side is a 37.5 millimeter subbase in South Africa. Then we've got the 26 millimeter aggregate. That's a bit coarser than what we use for our ASTM 57. And then we've got a variety of alternatives. Typically, the manufacturers will look at the grading or the opening spaces in their pavers, their permeable pavers, and give guidance as to which kind of bedding chip and jointing aggregate are used. And so there were several that were given to me as examples, and so I'm just showing examples of what I looked at. And then the software itself has what we call choking criteria. So the software basically goes through and looks at each of the layers as they fit on top of the layer below it, to make sure that the layer you place on top is not too fine and it sinks into the layer below. And so there are several criteria that are used actually by the U.S. Army Corps of Engineers for dam construction that we incorporated into the design software. So you can enter whatever you want in terms of aggregates, and then it will evaluate them and tell you whether or not they're good for choke criteria. And so a couple of these layers were debatable. It was close. Like we have a minimum of 5 and it was like 3.6. So it's close. And so we defer to local experience then to determine if you have some loss of aggregate into the layer below. And so then there's basic information as well, like bulk densities and porosity and things like that for the aggregate layers. And so the software allows databases to be built up with this. So if you have something you're using in Cape Town different than you're using in Johannesburg, then you could actually have databases for each of those locations and use local aggregates that are maybe unique to those locations, and you call them whatever you want. I started just calling them SA 1, 2, 3, 4, 5, South Africa 1, 2, 3, 4, 5 in my database. So I can call them up and use them again in the future. Traffic information is based on a ESL, but in so these are the number of vehicles, the design life, how long you want it to last, what kind of percentage of heavy vehicles do you have, how many ESLs per vehicle, things like that. And we still do use ESLs, and we have basic categories for low volume, things like parking lots and walkways and trails and things like that. We have a category 1 for just passenger vehicles. We've got category 2 for passenger vehicles and light trucks. And we've got category 3 for occasional heavy vehicles. And so the software will give you a suggestion for how many ESLs you should design for. If it's for more than that, then you need a little more details. You provide them on the left. The ones that you provide by ESLs, we convert to an axle load spectra. I don't want to tell you about the background details, but we use something a little bit different for the ASE method, but we still use this as the input values. There are AASHTO design parameters that are required. These are safety factors based on smoothness. So one of them is called a present serviceability index. Software gives you details and help menus and explains what all of that stuff is. You push the F1 button, it pops up and tells you how to calculate this and how it works. So anything in the entire software system, hydrologically or structurally, press the F1 button, it gives you help menu. So it tells you about what is an easel, how do you calculate it. Some of these graphics you've seen are in that help menu as well. Structural design thicknesses are then calculated. And so we calculate those values based on the ASTRO methodology, based on that input, and as well for the ASCE method as well. So let's go to South Africa for now. So what we did is we sat down with the South African Weather Service. They basically, Boson put us in touch with the appropriate people. We sat down and looked at the database information that was available publicly, and then what was available privately from the Weather Service. Determined that it was most appropriate if the Weather Service would process that data for us. So that was paid for a number of different locations. We basically have design storms for 12 cities in South Africa that give you the 2, 5, 10, 25, 50, 100-year design storms, and it gives us all of the daily rainfall data. And we've developed temporal storms, so time-based distributions over 24 hours for South Africa. And so these are your temporal curves that were developed to show you what percentage of rain on the vertical axis falls during what time frame in hours on the horizontal axis. That data was then synthesized and brought into the Permeable Design Pro system. And you can see on the right, we have storm types, and it gives you 1, 2, 1, 1A, 2, 2, 3, and those are North American. The TP 108 is one from New Zealand, and the ones below are South Africa 1, 2, 3, 4. And so on the left-hand side, you can see some of the data that's in the software that shows you what was used and how it's organized. We then have rainfall patterns and depths. So this is Cape Town. And so I'm just pulling up the data information from the software that shows you the basic information of where this came from. We can add new climate data if you wish to add. There's a feature to allow you to do this. It is painstakingly slow if you're doing this for 365 numbers in days. So it's better that someone with access to the software can do this, aka me. So then I can simply suck it into a spreadsheet and basically populate the database. So if there are other locations in South Africa that are desirable, if you can't find one that's close to what we've already got in there, there's the ability to add it yourself or to have someone else add it for you. If you wanted to do that, I would suggest you contact Boson and they could help you out and figure out what to do with it. We have rainfall patterns. And so all of this was then developed into rainfall patterns for South Africa. And so this is an output analysis that shows you what kind of rainfall we get at different locations, and then also how the structural design works in terms of the ASCE system. And so it basically takes all of those tables that you see in the ASCE standard and it fits them into categories. And so if you've selected some easels that are slightly higher, it will then bump you to the next highest category to increase the thickness of your subbase. All of the ASCE is based on 8-centimeter pavers, 50-millimeter bedding layer, 100-millimeter, 10-centimeter base, and then it calculates the subbase thickness, which is the structural capacity, and then the hydrologic capacity is also then evaluated. All right, so drainage design. How we do this is we basically bring everything together in terms of drainage design to be able to figure out the water balance. And so the system itself will go through and it will evaluate every 6 minutes, and in some cases 1.2 minutes, so a fifth of a 6th minute, for every hour during a 24-hour, 48-hour, 72 hours time frame, we'll develop a water balance. So water coming in, water coming from a contributing area, water going through into the subgrade, going through a pipe system. When does it start flowing in the pipe system? What is the slope on the pipe system? All that kind of stuff, and it balances all that for you. And then you can do some fine tuning of the what you want to do. So there's a page that says, well, you can assume that there's been water left in the pavement from the last storm 24 hours ago. So discount the volume by 50 millimeters because there's still water there. We can say run the analysis until the pavement is half empty or 10% full or whatever. And there's all kinds of other what if scenarios. How many pipes do I need? What diameter? Are they smooth? Are they coarse? All of this hydrologic calculations are completed. Other benefits, when you're finished, this thing will also allow you to output an AutoCAD drawing of the cross-section that you incorporated. And so whatever you choose in the design system, in terms of thicknesses, in terms of use of geosynthetics or pipes or whatever, it will generate an automatic AutoCAD design that you can copy and paste into your design details or drawings or shoot to a PDF or put out in an Excel sheet or whatever you want, along with all the other details that are there. The other features in this system as well, we can do things like what-if analyses. So for example, I'm designing a pavement that is going to, I told it don't get more than 90% full. So the kind of light area, the tan color, you have vertical axis is thickness, horizontal axis is design storm up to 0 to 100. And the tanned area on the top says, Dave said, design it so that you don't have water exceeding that depth. So never ever have water in the paver layer, and 90%, let it go 90% full. So this particular design is done such that it is capable of handling your 50-year design storm. So if the design storm is 60 years, then you're going to have a pavement that's too thin. And so I can simply take my cursor and touch that red line that's there and move it to the right, and it will scroll up the thickness of my subbase. So tell me, how thick does it need to be to accommodate a 70, an 80, a 90, a 100-year design storm? And it will ratchet it up for you. So it's kind of a nice feature. We can also look at things like pipe systems, for example. And so the graphic in the middle is the intensity of the storm. The top, the middle is the amount of water that's in the base and how it goes up and the storm ends and how the water then goes downwards. The one on the bottom has pipes in them. And so when it all of a sudden goes horizontal, the pipes are full of water. And when do the pipes start emptying? So this starts showing you how it empties basically over your design period. And so we can do things like design a pavement. So this particular pavement, I designed it. It's got no subdrains in it. It needs 15 centimeters or whatever in this case it's inches, unfortunately, but 15 inches of pavement structure. And I only it's good for a 3-year design storm. So I don't like that. So I'm going to go put one subdrain in 100 millimeters in diameter. What does that do to me? Well, that shifts the line to the right. So now my pavement structure I have is suitable for a roughly 13-year design storm. That's still not good. I want to do something a little more than that. So I'm going to put in 2 subdrains, and I'm going to make them 150 millimeter diameter. So I do that, and all of a sudden my line gets pushed further and further to the right. So now I'm up to almost a 75-year design storm. So I can still increase the thickness and make it to 100-year design storm, but at the same thickness, I was able to change the hydrological components of it. I mentioned already, all you got to do is move that red bar back and forth, and when you move the red bar, it will increase the thickness of your pavement and change the design storm, change your thickness of your pavement and make it compatible with what your goals are. Reporting in the software, lots of reporting abilities here. You've got all of the hydrological detailed information, what you selected, all of the criteria you picked, the subdrains you picked, the diameter, what slope they're on, all of that kind of stuff. All of those things are exportable, copy and pastable, output reports to Word, Excel, PDF, whatever you want, access to everything, as well as all of the detailed calculations. And so we spit out literally for every design storm, 2, 5, 10, 25, 50, and 100 years, every 6 minutes, or your choice. You can choose the time interval of 6 minutes or 0.1 of an hour, 0.5 of an hour, every hour, whatever. And it will summarize them all and spit them out into a grid that you can copy and paste into your own hydrologic software if you want to do to check things. Or I do it a lot to find out when there may be water ponding on the surface, or do I need to put in a bigger subdrain and all that kind of stuff. So all of that stuff is available. This is where you can get it, www.permeabledesignpro.com. There's a website where it can be purchased for US $190 there. If you are having issues or whatever with that, I encourage you to check in with some folks at Bosun that can help you out to make this. They are fully aware of how this all works and everything in South Africa, because they've been intimately involved in the process of us getting to this point with the software. Okay, so enough about software. The webinar is also talking about ideal ways to ensure success of permeable pavements in South Africa. And so I'm going to speak a little bit now about some key construction considerations, because we can do everything in the world best we can to design our permeable pavement system the way we want it to be. But ultimately, if we don't build it that way, it's not going to perform. And so this was some of the more difficult things that we ran into in implementing these in North America, is that everybody thought they could build a permeable pavement and they just went off and did whatever they wanted. And there's me shaking my head and, guys, you can't do that. Yes, you can do this, and et cetera, et cetera. And so it's not complicated. It is not complicated at all to properly construct a permeable pavement. It just needs some more bit of care and understanding of how to do that. So again, going back to the EWRI book, we have key construction features. And so in that book, There is a introduction. There is a introduction to all major permeable pavement types. There is a design section. There is a alternative design section, which are new and upcoming technologies. There is an entire section on maintenance, including costs and methodologies and all that kind of stuff. And I'll cover some of them as we go through the rest of the webinar today. So lots of good details. And there's also specifications. There's guide specifications that you can copy, and including actually in the Permeable Design Pro software, there is a location where you can copy guide specs out of it and edit them yourselves for use potentially that we used from the ASCE standard. So the best that we know how to build, and we put into these specifications, including densities and all kinds of stuff like that. So number one, make sure everybody knows what a permeable pavement is. And I don't just mean the people that are building it, I mean everybody else around it. So people that come in and landscape the thing afterwards, right? What are they going to do with their landscaping materials when they come in and they're putting a tarp down and dumping their wood chips or their whatever, their mulch and stuff, and not putting it on the permeable pavement? So they need to be aware of the situation as well. On-site preparation, we like to see mock-ups, and I do this. I do work for all industries in permeable pavements, and I always want to see them, pave a section of porous asphalt or concrete to make sure that everybody understands this. And when we, at the finish of the job, when we talk, we do what we call a hot wash. We go back and speak to everybody in the design, the labs, the inspectors, the contractors. Every one of them has told me that initial meeting, that pre-construction meeting, was key to making sure that they had success and they understood all of the elements we need. So ultimately, lots of different things with pavers and understanding the types you use, the thickness I mentioned already about minimum thicknesses, and how high do we place the pavers so that when we compact them, they go down to the elevation that we expect they're going to be. All of those details are important. We need to manage sediment on our job site. We need to make sure that things aren't dragging water and stuff onto our project site. I had 6 miles, 10 kilometers of permeable pavements built in Atlanta, Georgia. And they were building an apartment building near our site uphill, and they were washing out their concrete trucks on the road surface, and all of that sluddery was going around the corner and across my permeable pavement. So this was, post-construction for us, but pre-construction for the neighbors, who then were required to come back and rip up and fix some of the problems that they created on our permeable pavement system. On-site prep, basically, making sure that water runoff is going to be diverted away from the permeable pavement, be that from a barrier, be that from a berm or a trenched area behind it. We don't want water to run across our permeable pavement system like you see on the right-hand side picture, where it's basically just running onto our pavement. That's definitely not acceptable. Subgrade prep. Ultimately, you hear people say, do not compact the subgrade. I am a civil pavement engineer. I'm not a fan of not compacting my subgrade ever, because you compact your subgrade to provide you with structural capacity. When you do not compact it, it's going to be subject to potential settlements. Yes, it will have higher permeability, but if I have a soil that is not going to be very permeable anyway, I will take other features and build them into my permeable pavement design so that I can infiltrate water off the site, under a grass berm, under a golf course, under a playground, whatever. I can get water into the ground, but I just don't want to do it where I've got heavy vehicles driving or trucks driving on it. So ultimately, I encourage people to compact their subgrade. The base and subbase should be done as soon as possible to compacting the subgrade, because we don't want vehicles to drive all around the subgrade and compact it based on from their tires. We build underground check dams. We build underground features to slow the water down as it's flowing. That road I spoke to you about, I built granular dams like you see here on the right, covered with an impermeable liner that forced water to go downhill, up and over that berm, and then downhill and over and up another next berm to slow it down. Because I did not want to have water flowing freely through the permeable pavement system, because it would potentially erode something, and water will find a place to take aggregate. So we don't want that to happen. So on significant slopes, more than 3%, more than 5% for sure, we want to have underground features that are really easy to construct and will do wonders for your water balance and things like that. Use of things like geotextiles and geomembranes. I'm not a fan of these at all, ever, because it's complicated during construction. Contractors screw them up. They don't overlap them. They don't seal them. They do a whole bunch of things, and they're pain in construction. So I will go out of my way to not use them, But in many cases, especially when you're using water capture, then you have to. And so then there are ways of ensuring you don't puncture them during construction, that we weld the seams together, and all of these things are really important. You don't want to use anything that's too stiff, because then you can't work with it. And so again, lots of good guidance we have in our specifications for this. Under drain details, as I mentioned already about we put piping systems in. Well, we don't put the pipes in the granular base and subbase. We actually put the pipes below that. So typically they will be a big old drain tile or a PVC pipe with holes drilled in them, and we'll slot them into trenches in the subgrade below the permeable pavement. And at the outlet, if you look very carefully behind the guy in the red shirt there on the right hand side, you're going to see a bent curve update, or an up bend of the pipe. And so that's where the water exits. It exits at the elevation we choose. So you don't have to drive around on the construction site on top of these pipes, and they're not going to be damaged during construction. We put in observation wells. We put in things that will allow us to determine how deep the water is in the pavement, to take samples of water for quality testing, things like that. I like to put mine outside of the permeable pavement. The picture in the middle, you see one slotted into a paver. I've seen them put under the pavers, where you lift the paver, you open the drain, and have a look, you put the paver back. Again, that then introduces a hole of the pavement I don't like. So I typically do a design system more like the one below that. So the outside pavement one does the same thing like a regular one does, but it doesn't interfere with the pavement structure in its construction. And we also build cleanouts in some cases, be able to flush water out of the system if we have pipes in them. We want to make sure that the materials that we're using are clean. So in this particular case, we've got clean base and subbase aggregate. And this was given to me by a friend of mine in North Carolina, who ordered aggregate to be washed before it went to his job site. We don't want to wash, dirty aggregate dust into the permeable pavement system. So why put it in there in the first place? So we asked for washed aggregate. And so he checks that truck coming to his job site by using a water truck and saying, lift your back of your bed a little bit. And I'm going to spray water on the top, but if it comes out dirty and it looks like this, you're going back to the quarry because you didn't wash the aggregate. And so we don't want to start our pavement off with putting fines material into it. So washing the aggregate is usually a good idea. Of course, that also costs money as well. Base installation. So what are we going to use for those materials? Typically, it has to be local. You don't want to be moving aggregates from one place to another. It costs money for transportation, mobilization, for example. We look for local sources. Yes, we recommend certain kinds of aggregates in terms of sizes and quality materials and things like that. But ultimately, we always source something that's local. And it doesn't have to be the same all the time. You got to make sure it doesn't fall into the layer below it, and you got to make sure it has, some decent gradation. A lot of times, I sacrifice permeability for gradation because I like to have stable aggregate materials. So I don't like things all rounded, for example. That's doesn't make a good pavement structure. And then we also compact it to some target density. We typically do not use standard Proctor density measurements, things like that. We'll specify the rollers, we'll specify whether it vibrates or not, we will specify the type, the compaction, the energy that's being used, and then we will go out and do a number of passes or build a test strip to ensure it's properly compacted. So this is the guidance provided in Permeable Design Pro, the old version, the Astro version, which talks about doing a test strip using backscatter density on a nuclear gauge. And it just tells you how many passes you do to get it nice and stable. We've been doing a lot of work, and part of that construction we did for the ASCE standard was using the lightweight deflectometer to measure the density, in situ density after compaction of the aggregate and the minimum deflection that we will allow. And so this has been used now in ASCE standard for 4 years, but the industry also has commissioned some research that's being done in the US, in Oklahoma, I believe it is. They built a whole bunch of test pads. They're going to test them all with LWDs. They're going to provide guidance as to what we should potentially modify. And when they provide that guidance, we'll update the Permeable Design Pro guidance as well. So this is much more palatable and repeatable than using anything related to nuclear density gauges. And of course, it's much less expensive as well. Settlements, we don't want this to happen, obviously. Getting in a compactor in that corner may be a little bit difficult because we've got our concrete berms around the outside. When we are laying our pavers, we need to screed the layers to ensure we have a uniform layer across the pavement, no different than we would do conventional pavers. And so the bedding layer is an important layer in the entire process. And so for permeable pavers, we typically say 40 to 50 millimeter thickness, uncompacted. For conventional pavers, usually 25 to 30 millimeters kind of thing of sand material. When we screed our layer, it's really important not to put too much sand in if it's rounded particularly. So forget about that. It's not permeable, but again, 40 to 50 millimeters. And then we screed it to a common quantity. And I went out and I just bought a couple of pieces of pipe from my local home improvement place the last weekend. My wife went because she's the one that doesn't have the COVID. And I'm doing some self-made permeable pavement in my backyard. And so I'm screeding a small area using pipes that you basically lay down, and then you pull a wood mold or a screed over top of that to ensure that we have a uniform surface. We want it uniform. If it's going to settle, we want it to settle all uniformly. We want to make sure it's all providing the same uniform support for it. So screeding is an important component of this whole process, and it's not rocket science at all. You know, again, a couple of pipes with the right diameter, you lay them down, you screed the material across it, you pull up the pipes, you sprinkle in the remainder of your chip material where the screed rails were, and then you lay your pavers. And so I'm literally going to do this probably this weekend in my backyard. We can be power done, so we can have machine equipment pulling it. We can use actually small paving units that do this, but this is typically done manually, and of course it provides employment for folks and things like that as well, and can be done very easily and very quickly, keeping ahead of the people laying the paving stones. Edge restraints, critical, absolutely critical. You do not build any permeable or non-permeable paver system or brick system or grid system that does not have an edge restraint. Edge restraints can be anything from the metal L brackets you see on the left-hand side, the top and the bottom, for pedestrian applications from my driveway at my house. But if you have vehicular applications, typically we like to see curbs. They can be precast curbs, they can be cast-in-place concrete curbs. Do not put any paver system up against asphalt directly without having a barrier between them, an edge restraint. Asphalt's modulus gets really, really low in the summertime when it gets hot. And the permeable pavement system is very, very stiff. And so you want something in between them to ensure that it maintains a system and that you don't have movement of the pavers. That is a bad thing to have happen. If you can put your hand in and pull out a paver, that's a bad thing, bad construction. Making sure that everything is in straight lines. So we've got this guy's adjusting it here with to make sure we're meeting the specs. We're doing a mock-up of the system to make sure that the contractors know how to lay the pavers in a continuous uniform pattern. It looks better and it functions better. So it's not a rocket science approach here to make this happen. And a lot of them in our neck of the woods now are being machine laid because our labor costs are high. And so a lot of people are doing machine laid where you put a cubic or a square meter of pavers down using a piece of equipment. You know, so if you got a giant area when you're doing an intermodal terminal or something, then you want to try to do machine laid. But in most countries around the world, this is all manual laid. And by a variety of people, I've done a bunch of stuff in South America, and a lot of them are laid by women, you know, doing some work in their local city or town to, you know, as a make work project for people too. So that's nothing wrong with that. Cut pavers, hate them. Do not cut any paver unless you absolutely have to. And if you absolutely have to, never, ever cut a paver smaller than 40. My criteria is 40%. Many people use a third of a paver, but I won't let you put a paver down that's less than 50% of the area of a full-size paver. And you can do this. All you have to do is change how you lay the pavers. This is not rocket science. This is just a matter of understanding how you can change and interplace half units and put larger cut units in instead. This is so simple, so simple. And I always see these little slivers, and I hate them. They're not conducive to handling shear transfer across them. And so don't do this. Little slivers are a bad thing. These are one of those little details that you do not want to have done. The picture in the middle there, I took at our Ministry of Transportation offices where they did it in their parking lot. And this is like, no, don't do this. This is bad. Ultimately put a proper edge restraint and don't make slivers. Joint aggregates, usually looking to the manufacturers of the pavers to decide what kind of sizes and availability of joint aggregates are. You want them to be clean, hard, durable, chip kind of stuff, not rounded if possible. You know, river gravels that are crushed multiple faces. And ultimately, we want to make sure that they're put in the proper thicknesses to allow you to have a cross section that looks something like this. So in this situation, we have got now a proper constructed and built paving system that is going to allow the load transfer and the water to move through the system. And this was intentionally done like this so we could take a picture like this behind some plexiglass to show you what it's supposed to look like at the end of the day. Supplementary surface drainage, these are things like slot drains or curb cutouts that allow you to take water away from low points or surface water that can't get into the pavement system because the volume is so high in a big storm. We need to help it get into the underground storage system. So we've got some landscape features here in the middle between the parking area on one side and the asphalt on the other side. But under there is permeable aggregate. And so we're getting the water into the underground permeable aggregate. We've got the picture on the top right there is a small cutout. The one on the bottom right, this is a low point, so there's actually a catch basin there that will also move water to a stormwater pond if it's overflowing because there's so much water coming down in such a high intensity storm. This came from Nashville, where my sister-in-law lives, and so this is a bank, which is on permeable pavement all around the bank, and it's got some landscape features in the front, and that arrow is pointing to a very small round drain that is in the middle, that if it's overflow, it takes it to the street system, so the stormwater system on the street off the property. But their goal is to have no water leave their property, nothing at all. It all is basically accommodated on site. If we have utilities and potential utility conflicts, some utilities get all angry when you get water near their utility, but they will bury it in the subgrade anyway. So sometimes we're asked to wrap our utilities in impermeable liners, for example. So that will help alleviate that situation. Utility conflicts, again, we don't want the utilities to be in the pavement structure, and they should not be. But if they are, we got to deal with it. And so those are some of the basic things during construction. Finishing up now with a bit of stuff on maintenance. I'm getting near my time, so I want to do that, and then hopefully allow for some more questions as well. Maintenance is something that certainly everybody's still working on, and it's something that we have good research on as well. In many different countries around the world. I'm actually doing a project for the U.S. Federal Highway Administration right now to develop a new technical brief on permeable pavement design and construction. And we updated, I've got, 1,000 references on permeable pavements, something like that now, of which like 200 or 300 have been in the last 5 years. So we're updating some of that with some newer techniques and technologies. So ultimately, all pavements need maintenance. Doesn't matter what it is. We seal cracks, we fix concrete spalls, we do things to the pavement, we clean them. We do patch repairs in asphalt and things like that. So all pavements need maintenance regardless. The only thing different with the permeable pavements is that we want to ensure that we maintain surface infiltration. So surface infiltration, we typically specify most permeable pavements are 2,500, 2.5 meters of permeability per hour. So if I have a permeable pavement and I put a column of water up 2.5 meters tall, it will be gone in an hour. And so they're extremely permeable. We design them for 1/10 of that. We design them for something less, much, much less than that permeability. We define infiltration to be starting to be challenged when you get down to something like 250 millimeters per hour. That's still a huge amount of infiltration, more than the 100-year design storm anywhere in South Africa. So ultimately, we try to design for it, first of all. Secondary, we make sure that we've got good subdrains and outflow and things like that to be able to handle stuff. We've got test methodologies to inspect them, to determine what needs to be done to fix pavers that may be damaged, for example. And then we've got systems basically to evaluate surface clogging. So you may still, and you probably will, still get some stuff on the pavement surface. Whether it's wind blown or dragged on there or flowing off of the adjacent area, you will probably still get some areas that potentially are going to clog. It's almost impossible to clog an entire permeable pavement system unless you do something that's really, really, really stupid. And just smearing clay all over the pavement surface for some crazy reason. So there are ASTM standards, ASTM international standards for permeable pavers in terms of measuring permeability. And so that's a simple pipe with some plumber's putty. And each of my engineers involved in this has a kit like this in their trunk. And you've got a bucket with water, and you simply putty the pipe to the surface, dump water in, and measure how long it takes for it to go away. So and it's a standard little form. You got a little Excel spreadsheet that calculates permeability. And so there's a couple of little tweaks in that, but it's a standard. So you read the standard, you get this, you can do the permeability testing as a no-brainer. Cleaning the surface, lots of different things to clean the surface, right? These can be complicated and big pieces of equipment. And I'm showing you a few of those on the top. They can be relatively simple, things that you use around your house, a shop vac or a billy goat, which is that thing on the bottom left-hand side. The two pictures you see on the bottom right, I took these at the Bauhaus in Germany, where I was a month ago. This is like they call them Fugenbürste, and so you've got a piece, basically a wire brush on a stick, and you can literally go in and wipe the stuff off of your between your pavers. I took pictures of the advertisements there. Unkraut is or weeds, and so these are kind of things that are used, like pieces of equipment that you can buy for, I don't know, this was saying 60 euros or 70 euros, something like that. The little blade on a stick you see on the bottom is a weed remover, and so you can, for 20 euros, you can buy one of these metal brush things that will actually clean the surface and get stuff out of the joints. And so there are lots of simple things that can be used. This does not have to be rocket science. That stick there was, I think, 8 euros or something like that. So lots of these things are available and out there that can be used. If you're cleaning larger areas or some sidewalks and things like that, again, lots of easy ways to help improve the permeability. If you have very large areas, and we have taken in North America to using bigger pieces of equipment, primarily things like vacuum sweepers and whatnot. And so these are used mostly to restore permeability for highly clogged systems. The one you see on the bottom left, the Cyclone, is a little unit, and it does amazing. I've seen it work in demonstration projects all over the place. And this thing can suck the aggregate right out of the joint with all of the Schmutzdecke, the fine material that gets into the joints, and you can clean the aggregate and put it back in the joints and just remove the sediment. So it's awesome, absolutely awesome materials. Maintenance and repair of the individual pavers. You can do this individually with these units by removing them and replacing them if they're cracked. There's devices like this you can use. Quite frankly, 2 screwdrivers that pry the paver up. I've used that mostly myself to remove the first paver, and then after that, you just use a small crowbar to lift the pavers and remove them. So I'm going to give you a few slides that are just going to be continuous of showing you how a repair is done here. We're getting near the end. And so this shows you a settlement repair, a utility cut actually repair on a street roadway in California, and how there's guidelines to move these things. And so usually when I work on a permeable pavement design project for a client, we incorporate a maintenance manual as a part of the deliverables for this, and then we include a maintenance, usually an hour-and-a-half maintenance session, where I provide many more details than I'm telling you here. I don't have the time to spend that much on full maintenance here, but ultimately you get a guideline, you get a written guideline, and you get a training session on how to maintain permeable pavements, including doing utility repairs, patch repairs for settlements, all that, along with step-by-step. This is what you do first, next thing you do, next thing you do, next thing you do, next thing you do. So that kind of guidance is also available out there. So this is basically the repair process. Remove the first one, then remove the areas in the repair, screed and do your utility repair or whatever it is you wanted to do. Screed the material properly, nice and flat after you've done your repairs. And we talk about reusing some of the excavated materials. We talk about using things like control density backfill for small repairs and all kinds of more details. Again, I can't go through all those today. But then once you've done this, you put your screed rails in here. Those are manual. Those are lengths of pipe with the right diameter to give you your 40 to 50 millimeter screed. You put your aggregate down on top of them. You basically make sure it's all nice and well placed, and then you screed over top of the rails. This guy's using a piece of wood lumber to do that. You remove the rails, and you simply fill in the spaces where the rails were. In this case, they're using a trowel, a hand trowel, to make that happen. You clean out the layers beside them. These guys did not use a edge restraint because they were being very careful to keep equipment away from the edge. Sometimes we put a temporary edge restraint against the pavers that we don't remove to make sure that they don't migrate. So we don't want the joints opening up on those locations, because then if you do that and they start to migrate, you're not going to be able to fit all the pavers back that you took out, which is a bad thing. You can't do that. So then we've got our guy putting them back in, individual pavers, just like putting them in, small tap hammer, making sure they're straight in line, making sure they're on the nicely screeded surface. They've got a straight line that they put in there, so they can measure them against that straight line. They continue to replace them one paver at a time. A couple of guys here doing the work, or 3 guys here doing that work. Ultimately, they keep going. The hole gets smaller and smaller. Ultimately, it gets smaller again. And then finally, these guys are getting down to the last sections where hopefully, if you've done this all properly, when you hit the button and you hit the last paver, it's going to go back in. You then go over top of this and fill in the joint aggregate. So what they did is they brought it in with a small bobcat, a small lift unit, and dumped it into wheelbarrows where they just ran it along and sprayed it out with a push broom here, and you can see them applying it all. And then after finishing the whole thing up, getting it completed, and then we've got our final surface, and ultimately you can see the repaired surface versus the original surface without any difference between the two. So it looks a little bit dirty now because they just finished it, and I didn't want put water on it. It hasn't rained or anything like that. But ultimately, you're unzipping the pavement, you're zipping the pavement back up, and nobody knew you were there. And so that also provides a significant cost advantage to hard surface pavements like asphalt and concrete as well, because you can do that very simply and easily with almost no equipment. The key is to make sure you don't let the edges migrate inwards. And so I would take a small L bracket with a long spike in it and put the L bracket up against the pavers that haven't been removed, nail it in so that when you're doing your construction work and doing your excavation for your utility repair or your settlement repair, whatever it was, you don't let them migrate. Pull them up before you put the pavers down, and then you're off to the races. So it's really, really simple to do. So utility restoration guidelines, I mentioned already, this is just a short version of it, basically making sure that you don't have debris and stuff in the holes and keep away the materials from the excavated edge. How you remove the materials. If you're close to a curb, take out all the pavers. Anyway, good guidance are in the manuals that are available if you're going to, particularly for an agency that's going to do their own maintenance, or for potentially maintenance contractors, because since there's been so many more permeable pavements built in North America now and in Europe, there are contractors that specialize in doing this kind of maintenance, and so they're in the business of doing the maintenance of restorative maintenance for clogging and things like that as part of their business operations. Some lessons learned. So enough with the maintenance side of things. Ultimately, if you're doing things like pavement markings and whatnot, the picture on the left is from the Netherlands. The one on the right is from Harrisburg, Pennsylvania. You can use color pavers to mark the locations. So both of those are permeable pavement locations. The types of paint that you use, oil and latex, don't like to stick to pavers in general. So as much as possible, use a different color if it's available from your suppliers. And so we use them for crosswalks, we use them for skip lines, we use them for motorcycle parking locations here you can see, and you never have to paint them ever. So there's no maintenance related to these things at all. Ultimately, to maximize effective life of permeable pavements, limit things like standing vehicles that were going to leak oil, engine oil, and things like that on the pavement. It's not the end of the world. There are microbes and things like that in the pavement that break down oils. Ultimately, there are some geosynthetic materials that purport to be able to break down hydrocarbons. Disadvantage from my standpoint is that you have to put them in the upper layers of the permeable pavement, and I don't like to do that because they also can be a built-in clogging layer. And so I prefer it would be lower in the pavement structure if you're going to use those geosynthetics and things like that. Ultimately, keep things away from the area around it that are going to potentially cause it to clog. So like I said, the new construction with the concrete truck cleaning up his concrete materials on our site, that was a no-no. Limit heavy vehicle use on the permeable pavements. We built them to handle occasional load applications of heavy vehicles. And the one on the left I took from I think it was in Richmond, Virginia, and I watched the truck drive down the permeable alleyway, and it deflected the permeable pavement, and it came right back to where it was supposed to be. So it was elastic, which was awesome. There are applications that we've built for super heavy loads and large vehicles and mining vehicles and things like that, but don't do that unless you understand the basic concepts and have the tools to be able to design it. Finally, education is important. Things like power washing the pavement surface, people try to do this to clean them and they remove the aggregates. If you're going to replace the aggregates, that's perfectly fine. But if you're going to use it and not replace the aggregates, don't get too shallow on the power wash and too strong on the power wash so that it removes the entire aggregate from the pavement system. Again, if you're going to replace the aggregate, it doesn't matter. But ultimately, don't take the stones out unless you're planning on putting them others back in. And with that, so landscape material storage and stockpiling, things like that, signs like this. Some of these are mine. The one on the bottom is from Quebec. We put these signs up on permeable pavement locations to tell people what they should do, what they shouldn't do, and to educate the public on what we're trying to achieve in terms of water quality management, water quantity management. The one on the top there is actually from Hawaii, talking about how sustainable and this particular thing is for the rivers in the state of Oahu, in the state of, or the island of Oahu in the United States. This is one of my favorite ones from Northern Ontario. This is about 2 hours drive, 2.5 hours drive north of where I am on the Great Lakes. And this is a national underwater marine park. And all of the parking areas, all of the pathways, everything is a permeable pavement because this water is the cleanest you'll find anywhere. And so again, we don't want to have things being washed into the lakes up there because we have 3/4 of the world's fresh water very close to where I sit right now. So that's really important. So that's my last slide. So I'm close to time, and I think we've got a bit of time that we might still have on our agenda for some questions if there are. So I will turn it back over to Kurt to see if we have any questions. I'm going to actually stop my sharing as well right now, if I can do that.
Yes, Dave, we had a few questions.
Sure.
A lot of it's got to do with maintenance and life. What's the expected life of a permeable pavement? For what can you design it for?
Typically, we design like we would do normal pavements for 20 or 30 years. So these are initial service life. And so it doesn't matter what the pavement is, asphalt, concrete, whatever, you're going to end up probably having to replace some units. It might be cracked, things like that. So we intentionally design the pavement structurally for 30 years. So that's about the structural capacity and the traffic you have on it. In terms of clogging, that very much depends on the location of your permeable pavement. So I've got some that were designed that are underneath roofs of porte cochures that'll never see anything clogged on it, and they will last forever pretty much because there's no chance of clogging those. Those that are, we design it in situ for 1/10 of its initial permeability. Actually, we design it for almost 100th of its initial permeability. So we're assuming that we're going to get clogging in areas. We're assuming that the entire surface is not going to get clogged. So water will find a place. If it can't get in one place, it'll go find another place. And quite frankly, the best way to inspect to see if your pavement is functioning hydrologically is take yourself an umbrella and go out when it's raining and see if the water's going away. And if the water's going away, that's your inspection. You're done. That's your only tool that you need. If you need to do the actual testing, like I showed you, we encourage that when it gets below about 250 millimeters per hour of permeability. And that still is a huge amount of permeability. So the maintenance needs, I don't want to call it maintenance life because we design the pavement for the same life, whether it's from permeability or from structural capacity. But the maintenance needs will depend on the surrounding area. Did you properly design for it? Or is it the low spot where all the water comes and brings sediments to it? So most of that can be taken into account during design. And if you need to do some maintenance, it's easy. It's like I told you, the wire brush on a stick, you can go out and clean your joints because most of this stuff, the material that clogs the surface is contained in the top centimeter or so. And that's been proven from a number of research studies. So you just scrape the stuff off the surface and you're going to get permeability back. That's it. I mean, this isn't rocket science.
So you don't necessarily need a big machine to clean?
No, God, no. No. If you have a huge area, I mean, it's more effective to do that. But no, you don't need a big vacuum sweeper spending, whatever, hundreds of thousands of euros to buy something like this. If you have something, you can use it. But if you do not, I mean, anything, small areas, the small little vacuums that you use to clean your shop are good. Quite frankly, that wire brush or that thing called, I forget the name of it now, the German name for it, Maggie or something. It's a small electrical brush that has a rotating surface on it on an angle, and this thing pulls material out of the joint. And so you can literally follow the joints in some areas, and then you sweep up a sweeper, a hand brush, and a scoop, a shovel to get this out. I mean, really, this is not, education is very simple for this. It's go scrape the joints and put it in the hand brush, just if it's bad. The important part is identifying when that happens. So you don't wait till half of your parking lot has no permeability when you do that. I had one of those. I had a client who called me. They built a permeable pavement 20 years ago for a transit station near northern Toronto, Ontario. And I got there. There's no way. Everything is completely clogged. And they said, so what do we do now? I said, well, I'm going to get you a machine that's going to come here and clean out your joints and we'll replace your aggregate. How much is that going to cost? Well, the estimates for cost are in that ASCE book. I don't remember off the top of my head because my COVID is still making my head spotty. But I mean, you can use bigger equipment, but it's not a necessity. No.
Okay. Here's a question. How does permafrost affect suitability or performance of?
Okay, so a lot of people ask that question. So you're looking at permafrost or just frost? Like, I don't think you have any permafrost.
The question was permafrost.
Okay, because permafrost is something that's 100% full-time frozen. So I'm not sure if it's permafrost because that's a completely different animal, basically. We have a lot of permafrost in northern Canada. We have ice roads. I don't think you have any there, but if it is permafrost, it's well, interesting question. I've never had that one before. It's simply because I'm thinking about if you heat the permafrost, it will melt. If that's the question that's being asked. So heat usually comes from the ground below, but if it's permafrost, the heat can't rise from the ground below because it's permafrost. If it is frozen ground that we're talking about, or freezing causing heaving and things like that, there's nothing in a permeable pavement that's frost susceptible. So all the components are. You get water in the permeable pavement and it freezes, it will find a place to move because water expands 7% when it freezes. So there's lots of openings for the area to freeze into. So water is not an issue and cold weather is not an issue. I designed one permeable pavement in Thompson, Manitoba, which is on the elevation of probably north end of Sweden. And we built a big cistern hole and it doesn't rain there. It snows very much. It's a northern desert. So whatever moisture we get, we put into a hole that we dug, basically. And so unless you have very high frost susceptibility soils and you have freezing and at great depth, if the whole pavement freezes from the subgrade up, then that's the same problem you would have with a regular pavement. So there's nothing special related to permeable pavement. There's no issue.
Okay. There's a question. Do you have experience in permeable flexible pavement design like BROAG paving? I've got no idea what that is.
I don't either. Or
okay.
I'm sorry. I'm not sure what that is.
Yeah, I've got no idea what that is.
Off the top of my head, it's probably a permeable pavement system that may be related to some precast concrete blocks that have cables through them. I'm just guessing. So I'm sorry, I don't know.
Yeah. Okay. Then there was a question about aggregates. How do you get clean aggregates? Is it just?
Yeah.
Would you just speak to the quarry or?
Yeah, I mean, ultimately, you speak to a quarry. What they will do is they'll set up a pile and they'll use a fire hose or something to wash the aggregate pile. And so because the aggregates are open graded, the water will go through them. And when it goes through them, it will carry some of the fine material. And so you need to have that slurry go into a pond and dried and then considered to be waste material, because you may have 1 or 2% fines on the aggregate, but when you're putting in a lot of aggregate, you may end up with kilos of fines going into the permeable pavement. And you would rather not that happen, because you're actually reducing the permeability of your subgrade. Because what happens when it rains and the water goes through the permeable pavement, it will take those fines and it'll deposit them on the bottom of the pavement. So it will reduce the permeability of your subgrade. If it's sand, not a big deal because it's got high permeability. If it's clay, that's not a good plan. So you put up a pile, use a fire hose, or you put them in the back of a truck and you use a fire hose literally to wash the material out. You capture the water, it goes into a pond, the water evaporates, what's left is picked up and wasted or landfill. So that's how it happens. Yeah.
Right. So
no special equipment. No special equipment.
So that system, the question asked was bitumen, rubber, open asphalt grading.
As a permeable surface, it sounds like. There are a number of different asphalt and rubber systems that are permeable systems, and so that is a substitute for a permeable paver or a brick system, and that we have those actually in that ASCE guideline that I showed you, there's a chapter on those as alternative materials because they're not very common. They're used for in some cases running tracks and things like that, but they're not a highly common material used for permeable pavement systems. The vast majority of permeable pavements are pavers, bricks, then followed by asphalt, then followed by concrete. Those are the most popular ones, are 98% of the market, I would say, something like that. So these exist. There are other systems, and we do speak to them in the EWRI manual.
Okay. Right. I think we've covered most of the questions. Okay. If there's anything else, we'll write you an email.
If others have them and they send them to you, by all means, I'm more than happy to answer. Send them to me by email. I can respond to you. You can respond to them, or however you want to deal with it. I'm perfectly happy with that. So not a problem at all. I mean, the message from me here is, it took a long time to convince pavement engineers that permeable pavements could be built because the pavement engineers are taught to keep the water away from the pavement. That's the bottom line. And so it took a while to convince people. And most of the time, over the last 20 years, it's like I'm the only engineer in the room that's designing permeable pavements. That has changed remarkably in the last 5 or 10 years. I mean, almost every engineer is doing some of this. I was told there will never be a geotechnical engineer in the state of Hawaii that will ever sign off on a permeable pavement. And they've got 10 of them now, several of which I did there. So they're going from non-acceptance to reluctant acceptance to now actually doing permeable pavement design themselves. So things are changing, definitely. And it's, I mean, you go to Europe, I spent the last 3 months in France, Spain, and Germany. You can't go anywhere without finding a permeable pavement. Everywhere I walked, I found half the pictures I show you came from my walks in the last month in Germany or in France, and every grocery store and every Lidl and every Aldi and every bank parking lot and oh my God, they're like everywhere, absolutely everywhere. So you just need to start doing some and do them properly, and then you'll see the success, hopefully.
Mm-hmm. Dave, just one more question that came in just now, and that's got to do with geofabric.
Yes.
So the gentleman asked, so if you propose not using geofabric, how do you prevent the stone subbase from migrating into a sandy subgrade?
Okay, so good. That's a very good question, and quite frankly, first of all, the subbase aggregate are very large. And yes, we don't want them to prevent them from punching into the subgrade below. And so I'm okay on the bottom, and that's where I use most of my geosynthetics or geofabrics, and it's mostly for separation. I don't like using fabrics in the pavement structure itself, so above the subgrade. And people will put them in the middle of the base to say they can use less base. Well, I got to design for water as well, so I need the thickness there to have water in them. People put them in for the bugs eating the oils and things like that. Again, I consider them in the pavement to be a built-in failure layer, because more than once I've seen these things fail because of that. When we're putting them in below, we put down the impermeable liner, and then I'll put a fabric on the impermeable liner to prevent the aggregate from punching holes in the liner. So we're protecting that. So we're making sure of that. So yeah, I'm not saying don't use them anywhere. That's the place that I would use them as a separator layer, but only at the bottom, subgrade versus the material that's above it.
Okay. Right. Thank you, Dave.
I managed to make it through without coughing, so maybe my COVID is getting better. So I appreciate that from everybody on the call is spending time with me and making me be here today. So I appreciate all the health wishes from my friends in South Africa, that's for sure. And like I said, I'm available. I'm keyed into the EWRI and the ASCE stuff significantly. So if people have other non-conventional questions or something, again, contact Houghton here, and more than happy to help out with you.
Okay. Thanks a lot, guys. Enjoy the rest of your day.
Appreciate it. Everyone else too. Thanks. Enjoy your evenings. Take care.
Cheers.
Bye-bye.